So we started a new example last time, which is diffusion with what we call heterogeneous chemical reaction. So when we say homogeneous in reactions, we refer to reactions that are happening everywhere in the volume, and that typically results in a volumetric term in your partial differential equation. You have a source or sink term that is sitting there parallel to the entire equation, because things are happening at every point where your partial differential equation is also valid. Now, when we have what we call heterogeneous chemical reaction, it's happening on some boundaries and surfaces, so it's essentially a boundary condition. And in this case, this is very often the case in catalyzing reactions and processes where you want to increase surface area. You're going to place a bunch of spheres that actually have whatever catalyst attached to the surface. That way, you distribute that catalyst all over the place. Okay? So you evenly distribute it, and you also increase the surface area. So if you take the same volume, you can just do that exercise. Actually, if you take a cube volume, right, and you can then, that cube, you can break down to small pieces. And you can calculate the surface area and how it increases as you increase the number of small pieces per side. Let's say that you're breaking it into n by n by n cubes, right? So see what happens as that n increases and how surface area actually increases. So basically that's used a lot in these in these applications. So what's happening on this surface? So I have a zoom in. So as I have species A come into the surface, 2 moles of it, 1 mole of B is leaving that surface. Okay? So that is happening on each sphere. So when I actually zoom in next to the surface, I kind of lose the sight of curvature, just like us thinking that the Earth is flat. And it's actually not. So basically we here assume that there is sort of a film of thickness delta, and within that film we are monitoring this reaction. Okay? So I'm going to hypothesize that this film on the surface is stagnant film, right? And I will have this mainstream coming in, sort of in this z direction. 2A is coming in right to the surface, and B is leaving. So at boundary z is equal to 0, I'm assuming that I have a given concentration of A that is maintained by sort of a flow around these spheres. So we know that flow is very effective a little further away from the solid surfaces. Right close to the surface, the velocities get very low, so things get really stuck, and like I don't think that this mainstream would be effective, and that's basically this thickness delta that I'm talking about. Right? But outside of the sphere, velocities are larger, and those basically manage to take everything away and maintain certain concentration XA0. And then as z is equal to delta, XA instantaneously gets converted to B, so XA that momentarily as in on the time scale of the process, that's happening really fast compared to everything else. So XA is 0. So those are my boundary conditions. And then what I know about the fluxes here, okay, is that NBZ, so flux of B overall is opposite of flux of A, and it's 1/2 of it because these are molar fluxes, and 2 moles of A get converted into 1 mole of B. Okay? So that actually helps a lot, because if you remember, our biggest problem in figuring these problems is that in, for instance, term for NAZ, let me actually write it down. So I know already when I do the shell balance, since there are no volumetric terms, it's like dNA dz has to be, derivative of n has to be equal to 0. Okay? So that we already had before. And the problem is, what is this NAZ? So NAZ has that Fick's law term, So I'm looking at the z component, otherwise I'm normally having a gradient of xa here. And then I have plus xa multiplying the sum of all other fluxes. Okay? And what's it, when I refer to convection, so I have in diffusion I have convection, and this is not necessarily the same convection as as my momentum transfer convection. Some of it is kind of break it apart, but some of this convection is actually happening just because if I have flux of B, some of those molecules of B will kind of bring along A, right? So some of it is happening simply not just because of the gradients of, or the chemical gradient of A, but some of it is just happening because some other molecules might shove my molecules of A along. That's essentially what intuitively this means. Okay? And that poses problem because it's coupling. I'm coupling the two. That poses a problem in solving mass transport. And this is basically what makes it complicated. So in every problem, I gotta figure out what to do with this term. First thing you ask yourself, hey, can I somehow make it zero for practical reasons? Can I assume, for instance, that xa is really, really small, and that kind of makes this zero? And then I have only fixed law, and that's easy to solve, right? And then if not, then ask yourself, hey, is B maybe stagnant? Maybe I can make B zero. Go down the cases, just for your own sanity in solving these problems. So basically, is B stagnant? But B is not stagnant here. I'm producing it. Therefore, it's a significant, relatively significant flux of it, right? So I can't. But that reaction allows me to specify what NB is. Again, the complexity of the mass transport problems is this term, really. So what do you do? How do you express this? Do you take convective fluxes into account at all? Okay. And if you do, can you somehow, do you have to take NB in account, or how is it related to NA? And then you can proceed to express NA in terms of XA and actually solve your differential equation, because most often your boundary conditions are expressed in terms of XA. We do have boundary conditions that are expressed in terms of NA as well. There is that equivalent of the Newton-Coulomb law, for instance, but you still depend on concentrations in that case. So that's essentially the complexity of these problems. All right, so let's get along now that we actually know what NBZ is. Okay? Then this has to essentially be 1/2 of NAZ. And my NAZ, I have NAZ term and here NAZ term. So basically my NAZ is multiplying 1 minus half XA, DAB, DXA, DZ. So basically this tells me that NAZ is equal to minus 1 over 1 minus 1/2 DXA DZ. Oh, well, where am I writing that? XA here. Bless you. And I'm gonna squeeze this CD up here. Now, I know that from shell balance before, I don't need to solve it. Again, that dNAZ/dZ is equal to 0. So from before, we know already dNAZ/dZ is equal to 0. And by the way, let me just put that side note. If I was in cylindrical geometry, for the equivalent shell balance with no reactions, hi, hello Anaconda. I didn't mean to open you. That's a different class. Cylindrical geometry. For cylindrical geometry, I would put the dz. What you're going to get is something like this, okay? Accounting for the curvature. And for spherical, ddz r squared na. So if you do classical shell balance that we do, depending on geometry, so in a straight geometry, you just have dna dz is equal to 0. In cylindrical and spherical, we have to take to account for curvature in one or both directions, right? And that's why you have r and r squared term. Okay? Essentially because your areas are changing and your na is per area. But in a coordinate system, as you get further away, your areas in this little shells are changing from one position to the other. Okay? R. I'm talking and writing, always a challenge. So just mentally have that, put it on your cheat sheet or something, and there are problems in chapter 18 for pretty much every type of geometry, but that's what you would be solving here. The problem in itself still remains, well, what is your, in this case, it would be NAR in terms of the other fluxes, or what is the NB in terms of NA, okay? So the rest of the problems remain the same. So that's just a side note. Now let's get back to solving this problem. Okay. So I have that my derivative, so therefore my 1 over, whoops, wrong color. Say dxa dz has to be equal to constant, right? And since we are assuming in these problems that CDAB is equal to constant, I'm just going to write the 1 here and basically incorporate that into this constant, whatever it is. Okay. So I'm going to call that constant, and let's, now that we're at it, let's multiply it by 2 and put this 2 over 2 minus xa. And I'm going to call that constant C1. So in terms of integrating this is already in good shape. Oh, well, may as well get rid of a 2. Then it's going to be in a good shape because that 2 can get to that constant on the other side.
What about the negative?
Negative I need to integrate because I have, or I can just write 1 over xa minus 2, right? But since typically xa is a small number between 0 and 1, I'm going to leave 2 minus xa because that makes it positive, for sure. So basically this here is equal to C1. I could have put, let's see. No, it's just ln. Minus, yeah, minus gets, I don't know, really. So, no. Let's rewrite. I'm trying to shorten my writing, and that's not productive. Okay, so I'm going to put dz on the other side. So if I had ln of 2 minus xa, and I did a derivative of it, Okay, I will have 1 over 2 minus xa times minus 1 times dxa dz, correct? So I can remove the z here from this, but then basically this is precisely in the form it needs to be to integrate. And when I integrate the other side, c1z plus c2. So my boundary conditions I have them at z is equal to 0 and z is equal to delta. If x is xa 0 and xa is 0. So that gives me two equations for two parameters that I don't know. So I have ln of 2 minus xa0 is equal to c2. And I have ln of 2 minus 0 is c1 delta plus c2. So c2 is already given, and c1 from here is 1 over delta ln of 2 minus xa0 divided by 2, which is that 1 minus 1 half of xa that I had before. So when I get that into my equation here, so those are my c1 and c2, I will have, so c2 is ln 2 minus xa0. When I put that negative and on the other side, I'm going to have ln of 2 minus xa divided by 2 minus xa0.
The hour term should be flipped because you are moving
This one?
CQ to the left, so it should be negative.
Minus?
You have to flip the numerator.
Ah, okay. So it's minus that, or 2 over this.
Yes.
Yes. This was a test if you were paying attention. No. Ha ha ha. And this is equal to, Did I mess anything else up?
No, I'm just saying that your computer might shut down anytime.
Uh-oh. So you can just volunteer to go get my... It's a Mac. Anybody has a...
I haven't the new Mac.
Okay, yeah. Then you don't have to. Thank you. My Mac is not this new. Anybody has an older new Mac? Older new Mac? Middle-aged. Middle-aged. Thank you, thank you, thank you. There we go. All right. So when we put this back, is equal to 1 over delta So then you put this 1 over delta to, or z over delta rather, to the exponent. So this is ln of 2 minus, and I'm going to flip the sign of it, minus z over delta. So because this is multiplying this ln, right? So this is z over delta, and I put it to exponent, and I also flip this with a minus 1. And then basically 2 minus xa over 2 minus xa0 has to be equal what's left in there. Another way to write it would be, and that's what apparently what textbooks suggest, is that 1 minus 1 half xa, and I divide by 2, is 1 minus 1 half xa0 to 1 minus z over delta. So basically I transfer things that I know and things that I don't know. That's essentially the solution, a little ugly, but it's still a nice formula. So to get what actually my flux is, I need, remember, dxa. So basically, in order to get flux, I also need to figure out what is dxa dz to get naz. And if I do the derivative of the other side, so basically I can do the derivative of 1 minus 1 half xa, so minus 1 half dxa dz as that 1 minus 1 half xa0 and then ln of 1 minus 1 half So the first part comes from, whoa, hi. The first part comes from taking a derivative of this power, something to the power of z, but then I have a function of z that is not just z, it's 1 minus z over delta, and derivative of that is minus 1 over delta. All right, dot, 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 my NAZ, which is minus 1 over 1 minus 1 half xa, CDAB, dxa dz, is equal to, I'm just going to plug it all in, 2 CDAB over delta ln 1 over 1 minus 1 half xa0. So in these problems, I typically do want to know the flux. What is NBZ? Minus 1 half of this. So it's in opposite direction, and half of it. So these molar fluxes are given, and they're fluxes near to the surface, right? So they're not necessarily, so this is local flux of A near catalytic surface. So how would you upscale that? So I have a surface area of the sphere and number of spheres divided by volume, and that can actually give me a volumetric term in my partial differential equation if I needed one. Okay? So essentially to upscale, NAZ times surface area times number of spheres divided by volume. That can give me volumetric reaction term in my PDE. So that also hints that there is two ways to solve these problems. You can go through boundary conditions, or you can kind of upscale if you know how to average whatever is happening on the small surfaces and add a volumetric term that replaces what's happening. And when we have a lot of surfaces, that's something that we'd like to do. Sometimes you can also, so if you have something that is relatively thin, but what's in cooling problems, loss near the area, it's to have cooling fin, you kind of increase the area by multiple fins that you have in a geometry, right? But you can actually still solve that as a one-dimensional problem if you figure out how to this loss through the surface, how do you put it as a volumetric term in your partial differential equation? Or you go with the detailed analysis and actually accounting for that surface properly. So there's always kind of two ways to do this. All right. All right. So I'm going to move on and hopefully get through one more problem. And this is 18.5 in BSL. This is diffusion into a falling film. So I have a surface. My situation is the following. I have, this is my x is equal to 0, my delta, there's a film of thickness delta. And there is, it's moving. And this is my Vz of x that I know how to get from my first part of this course. Okay, so I have a viscous film. So viscous flow within the film. And we assume we know Vz of x. However, I have actually also introduced gas, some gas. So this is my, I'm going to call this B. The whatever is flowing will be B. And I'm going to introduce into the stream a gas A. And this gas A at this x is equal to 0 this gas A is C. I have concentration of it given with as Ca0. So with the flow, it's constantly replenished. Just at that location. So I'm wondering, okay, well, how will this actually diffuse into this viscous film, knowing that actually viscous film is kind of dominant in pulling things down. So I will have some of that if you think about the concentration. Oops, no. See here? It's going to kind of be maximum and kind of fall down as it goes into the film. And I'm just wondering what that is. So gas A is soluble ever so slightly in B. And overall penetration of A into B is small compared to the thickness, film thickness. Okay, so what do we have here? Let me take another page. So I have space. When I do the shell balance, I have this shell that has both x and the z direction. I didn't name it, but it's a z. So I have my little shell, okay, and this is my z, z plus delta z. This is my x and x plus delta x. And I have sort of dominant convective flow in z direction. And somewhat less dominant flux in x direction. So when I balance the two, okay, I'm going to have stuff that is coming in through the x boundary, NaX, evaluated at x, times area. So this is delta z times some width in the other direction. I'm going to put it in because I want to have areas. Minus NaX at x plus delta x, same area. And then in z direction, I have NaZ in z, delta x times W, and NaZ at z plus delta z in the same area. All of that is 0. So my standard procedure is to divide by volume of this little shell. So delta x, delta z, delta y, delta x, delta z, w. And that will give me minus n x, x, x plus delta x divided by delta x minus nz lots of sneezing. Is it allergies or is it this 35 degrees this morning? Or both? Huh? So when I take the limit, I'll get my differential equations. A differential equation plus dnz dz is equal to 0. So before we had just dnaz dz because we had only one direction of things moving, and now I have two directions. So that's the main difference. Now, what is my NA? This is, and look at me, I just dropped A's at some point. I'm like, this is a lot of writing. And AX and AZ in this alphabet soup of subscripts. Now, my NA is minus CDA B XA plus XA and A plus NB. That is my definition, essentially, that I'm using in all of these problems. So when I look at NAZ, so I have Z and X components. Let's look at the Z component first, because that's my dominant flow. It's minus CDAB dXA dZ plus I can also write, so what is my NA by definition? So this is Z, where my convection of the just moving viscous flow, the fluid is dominating everything. So I'm okay ignoring this part in Z direction. Okay. If I have a little bit of motion of A in Z direction, I'm really thinking that, hey, it's dominated by actually viscous film pulling everything down. Okay, diffusion doesn't have time to catch up. It's probably 2 orders of magnitude smaller. So this is going to be ignored since convection dominates in Z. And then this CA, this is CXAVA. This is CXBVB. So this is, I can take CXA times XAVA plus XBVB. What type of average is this? Both of them are arithmetic, but one is using molar fractions and the other one is using mass fractions. So this is what we refer to as V star.
Is it VA or VAG?
This is XA here. So VA, Z, Z, yes.
So V star or V star?
I just introduced. This is all supposed to be in Z direction. So this is V star Z. So this is basically CA V star Z, and that's, I'm gonna approximate with CAV Z. again, I'm insisting on vectors this morning for some particular reason. So we are assuming V star is approximately the same as V. That's often made. That assumption is often made for dilute solutions. It's not a bad one. The reason why I'm doing this is that this I actually know. Okay, I know this.
For what case would the Z star be very different from DZ?
It's rarely very different. Those are small differences, and we typically have relatively small fractions. That's not a problem. It's ever so slightly moved from each other, but like if you get 5% difference, so in the grand scheme of events, this one I know how to compute. Okay. Okay. Now let's look at NAX. That is minus CDAB dxa dx plus, I'm going to immediately do this derivation that I did right here. And now I'm actually going to, so for x direction, I'm going to ignore the convective part because that one is dominated by just the diffusion. So this one is dominant, and this one is ignored. So that is simply minus CDAB dxa dx or minus DAB dca dx. No, remember that my boundary conditions are in terms of CA. So I'm just, whether you formulate things in terms of XA or CA is typically fine either way. But if your boundary conditions are given as one, then go stick with that one. Okay. Okay, so I now put this and this into my shell balance. I'm going to call that 1. So my 1 gives me ddx of minus DAB dCA dx plus ddz of CA VZ of x is equal to 0. And I threw in VZ of x on purpose. I don't have to do a derivative of that. I just know what it is. Right? So VZ of x is something that I know. It's in the form, it's that parabolic form. So I'm just going to take it as V max 1 minus x squared over delta squared. So it doesn't depend on z. So I have a first order derivative with respect to z of CA times something that is dependent on x is equal to, on the other side, essentially DAB, second order derivative of CA with respect to x. And that is essentially a variant of heat equation. If this was constant, then it would be a clear heat equation. but it is very similar to it. So what I have to solve is the following. So I have Vmax times 1 minus x squared over delta squared. dCA dZ is DAB what on earth did I do now? Okay. Okay. You know, I'm just going to open a new one. All right. This does not like a tilt. That's what it is. So it was tilted here. Do you mind if I write this down? Vmax 1 minus. Do not tilt this in any. It's very sensitive apparently to. Okay. And we have at z is equal to 0, Ca is equal. We need that boundary condition, so I'm adding something at the very top for z is equal to 0. And for x is equal to 0, those are the ones that we mentioned. And x is equal to delta. So I'm also going to add the boundary condition at the solid wall. Nothing's going through it. So this we will actually solve for assuming this x squared being relatively small and this being just Vmax. Then I actually have a form of a heat equation. And here it's in terms of z and x direction, but next time we're starting something that I call time-dependent problems and dimensional analysis. It's going to be equivalent, so we're going to solve this general equation, and there is going to be a lot of equivalent problems that are solved by basically having solved this heat form of equation. Okay? And the only thing is that the form of solution changes based on the boundary conditions. Okay? So we're going to solve two versions of it, and it's going to be applicable to this problem and a lot of other problems that we have, basically in momentum, mass, and heat transfer. Okay? So that is our introduction to that.